Hello everyone, and thank you all for coming. Just for the confusion of the affiliation, because in the book it says that I'm from University of Oxford. So I just moved to Polytechnic University of Madrid as a lecturer, but most of the work has been done during my PhD at the University of Oxford. Part of our collaborators are also like Mike Mills from Ohio State University, and we are getting funded. My PhD was funded by EPSRC in England. But after my PhD, the US Air Force was interested in the project, so they're continuing funding the project until 2021. So what I'm going to talk about is basically a new kind of deformation mechanisms that are appearing in the materials that are used in the jet engines in the airplanes. These materials are nickel-based superalloys, and because they are facing new range of temperatures, new deformation mechanisms are appearing, and we need to study them to make better materials. So this is the structure of the presentation I'm going to give. First, I'm going to give a brief motivation and the objectives of the project. Then I'm going to jump to some experimental studies I did just to give you a background of the physical processes in the deformation mechanism. And then I'm going to move directly to explain the continuum model framework we developed. And finally, I'm going to present some results using that model and some of the technological applications we are working on now. So let's start with the motivation. So the problem that we are facing is, as I said, in the jet engines of airplanes. These jet engines are running hotter and hotter and hotter because of reducing the CO2 emissions. Because if the engine is running hotter, the cycle is more efficient, and then the CO2 emissions are getting lower. The problem is now the materials that are used in these jet engines, the nickel-based superalloys, are facing higher temperatures. And if you have a look here at the deformation map here, as you are increasing the temperature, there are new deformation mechanisms that are appearing that they were not the target in the past for research because we were not in this temperature regime, but now that they are critical because we are getting in service in this temperature regime. These deformation mechanisms, they are really complex because they couple diffusional processes, so chemical changes, with a standard plasticity, dislocation shearing. And among them, the most important one is the micro-tuning mechanism, which I'm going to explain next. So what is the difference between this micro-twin mechanism that I'm going to explain and the mechanical twinning that everyone else is studying in other materials? So mechanical twinning is basically, this is kind of this micro-twin mechanism that I'm studying. So they are really thin bands of a few atomic layers, and they're forming in parallel sets. And the difference with mechanical twinning is if you have here a mechanical twin, basically is formed by continuous paths of partial dislocations that basically what are producing is the same crystal structure, but just rotated in FCC, for example, will be 60 degrees. But the lattice structure is again perfect. The problem in nickel-based superalloys, we have aluminum and nickel atoms together. It's not just one kind of atom. So when you share the material with partial dislocations, you are creating ground neighbor structures that are high energy structures that the material doesn't want. So because you are creating these high energy structures, the stress required to continuously shear in the material to create the microtwin is much, much higher than in the mechanical twinning. So you need some kind of atomic diffusion or reordering to make this going back to the low energy state. So that's why this mechanism is only happening at high temperature, in difference with mechanical twinning. So the kind of the objectives that this project is aiming is basically to understand this diffusion phenomena and couple this with deformation, plastic deformation. In order to do that, we first did some experimental studies to understand the underlying physical processes. Then we developed a physically based continuum model which takes into account the concentration, which this part is really important because by taking into account the concentration effect, we now can, with these models, can now develop new grades of chemistries of alloys with superior properties. So I'm going to start with the experimental studies first. Basically, we got one of these superalloys single crystal. We focus on single crystal because we wanted to delete the effect of the grain boundaries and just focus on the crystal plasticity. The single crystal we use is MD2, given by Siemens. We got 3 different orientations, 001, 011, and 111. And we did creep tests at different stresses at 800 degrees. in tension and compression to see which mechanism was activated in each of the conditions. And we found that actually the material that is creeping at higher creep rates is actually the material that is twinning. So we can see the activation of microtwins at 001 orientation in compression and 011 orientation in tension. And the microtwin mechanism, as you can see here, is not symmetrical as it happened with mechanical twinning, because we did the opposite and we couldn't see in tension or in compression in the same orientations. So we got one of these samples into a transmission electron microscopy at the atomic scale, because we wanted to study like what was going on during the deformation. And this is one of the microtwins growing. It's a microtwin embryo, this ledge here. And we found that actually the microtwin was segregated with cobalt and chromium. Cobalt and chromium, there are studies in the literature that show that they lower quite a lot the stacking fault energy and the antiphase boundary energy of these kind of faults. So our theory is that as the dislocations are moving forward, creating these faults, they need to segregate new concentrations of cobalt and chromium to eliminate these ground neighbor structures. And this is what we are trying to model in the next step. So I'm going to get into the continuum model framework. The model that we need, clearly, it needs to solve the chemical field around this twinning formation. It needs to couple this chemical field with the plasticity that is happening, because as I said, the chemical composition is changing the stress required for the dislocation to shear the precipitate. And finally, we need to account for the material changes as the phase transformation is happening, because as the microtwin is forming, the new material doesn't have the same elastic properties than the parent phase. So we need to take all this into account. So we need to couple together thermodynamics, crystal plasticity, and phase transformation theory in a unique framework. So this is a summary of the rheological model. Basically, we take into account the elasticity of all the different phases that are at the beginning. We will just have parent phase, but as the material is deforming, we will start to create the twinning phases if the conditions are favorable, and the stress is a combination of all these phases together. In terms of plasticity, we take into account the three different main deformation mechanisms in superalloys. So octahedral slip, which is just full dislocation shearing the gamma and gamma prime precipitates. Then cubic slip, which is a mathematical artifact for continuum modelers to take into account the dislocation jumping the gamma prime precipitates, the cubes. And finally, we have the phase transformation, which is basically the microtwinning mechanism. And each of especially the phase transformation, this damper, the constant of the damper will depend on the chemistry that is happening locally. So if you are pulling the material really fast, your chemistry is going to be different than if you pull it slower. So we have 4 different configurations, as always reference and current configuration, and we have created 2 different intermediate configurations, the intermediate transformation configuration where we set up our plastic flow rules for the phase transformation, and then a second intermediate relaxed configuration where we set our power law for cubic slip and octahedral slip. So the Helmholtz free energy of the system will be a combination of the parent phase free energy and the transform phase free energy, scaled by the fraction that we have of each of the phases. Each of these Helmholtz free energy of parent and transform will have a combination of mechanical free energy and chemical free energy. The mechanical free energy is coming solely from the elastic energy of the material, which is loaded. And we are taking here also again into account the elastic stiffness of the parent phase and the transform phase. The chemical contribution to the Helmholtz free energy is basically dominated by the stacking fault energy, which is the difference between the free energy of the twin system and the previous parent phase. And it's a concept that metallurgists use for their models, actually, more than continuum modelers. Okay, so if we start with the first and second principle of thermodynamics, and we have here the stress power for the plastic deformation, the transformation, plasticity, and the elastic part. Then we combine that together with this quality here, and it gives you the Clausius-Dunham inequality. If we derive with time the Helmholtz free energy from the previous slide, we get to this, after doing a bit of math, we get to this function here, taking into account mass conservation because we are not creating cobalt, chromium, or other elements in the system. So it needs to be mass conservation between both phases. We combine this together with this function into this Clausius-Dunham inequality, and we get to the, after deleting some of the terms, we get to this dissipation rate equation, where we can see here the dissipation of a slip, the dissipation rate of the transformation, and the dissipation rate of diffusion. We will forget now for the diffusion part because this will lead directly to the Fick's law basically, but by looking at these two terms, we can get the driving force for these two mechanisms. So let's start with the slip system. So if we have cubic slip and octaedrical slip, we include the velocity gradient just as a standard crystal plasticity theory. We include that into the dissipation rate, and we get to the end to an equation where we have the plastic multiplier multiplied by the driving force for this mechanism, which is the Resorser stress. And we have included this driving force into a standard power law, and you get this standard power law equation. But this becomes more interesting for the transformation, because the transformation, the velocity gradient basically is a compound, can be a compound of a shear strain plus a volumetric change. But in the terms of microtwinning, we don't have volumetric change, so we will have just the shear strain. If we include that into the term for the dissipation rate of the transformation, we get to this driving force here, multiplying the plastic multiplier for mass transformation. And we can now, so taking this into account, this equation that relates the free energy of the parent phase minus the free energy of the transformed phase, which is the stacking fault and the change of elastic energy, because it has different elastic constants. If we include that into the driving force here, we get to this kind of power law, which is the same than the plastic one, but it has a kind of back stress, which is related with the stacking fault energy, which depends on the chemistry. So, and finally we have a standard hardening law, but the important part here is that this stacking fault energy depends on the chemistry, and it's changing during the whole plastic process, and it depends on how fast you are pulling the material, and it depends at which temperature you are pulling, because the diffusivities and everything will change. So all the velocities of the chemical going to the plastic regions is going to change. So we need to solve the diffusion field at the same time of the plastic field if we want to include the chemical effects in this part. So the diffusion field, basically, as I said here, the chemistry, so this is the stacking fault energy, again. So the stacking fault energy depends on the chemistry. This will be an unsegregated fault, so without changes in chemistry. You can see here like a high energy coming from the ground neighbor. This is data from the literature coming from DFT. And then if you have a fully segregated fault, it will be a much lower energy fault, so the dislocations will start shearing much faster. So there is a driving force, we need to solve the diffusion field, and there is a driving force that is not coming from the standard Fick's law, so it's not just the gradient of concentration, but it's also the gradient of chemical potential from the stacking fault energy that you can see here. So our diffusion equation is enhanced by this term that we need to take into account in the solver. So we have taken advantage of the similarity of diffusion equation with the heat equation. We have used Abacus solver for the temperature, and basically just by linking the equivalent of the heat diffusion to mass diffusion, we have been able to code just UMAT subroutine for heat transfer and be able to solve the whole process in Abacus coupled with the mechanical part. It's a non-local problem because as the twin is growing, you need to take that into account when you are rotating the element. So we are also taking into account kind of non-local model, because for every element we check if the surrounding one has twin or not. So the twin can only propagate into the direction of a slip. And I'm going to present now some of the results related with all this continuum framework. So this is the creep test that I presented at the beginning. So we have used the compression part for calibration of the mechanical constants, and the tension part for validation. So we got good agreement between the creep curves. The only part that is getting away from the experiment is this last part in 011 and 001 in compression. This is because microtuning produces a increased material embrittlement at the end stage of the creep, and we are not taking into account any fracture in the model. So if we want to model this last part, we need to take into account kind of a fracture model. So it shows good agreement with the experiments. Now we wanted to go to the micromechanics and try to model what was happening when the twin is growing. So this is a brief example of a twin growing. So you have a first ledge growing where the dislocations are just shearing the material, and then you have a much faster second step dislocations because the segregation is already there, and when the twin is growing, in the middle of the twin you don't need segregation anymore because it's a perfect structure. The ground neighbors are only at the interface. So this is captured by the model, and the nice thing is in the concentrations, you can see at the beginning where you have an enrichment of cobalt and chromium concentration, then you have the second partial coming here, but as the twin is growing, the concentration in the middle of the twin is coming back to normal, to the parent phase, because the ground neighbor structure is just concentrating at the interface. So we have compared that with some of the results of the experiment. So this is taken by TMEDX, and when you make the same plot on the computational model, you get the same kind of concentration peaks levels. I have to say that the chemical part, there is no calibration parameters. Everything is taken from basically thermocal and concentration from the experiments. On the mechanical part, of course, there is calibration parameters that I have calibrated before in the previous slides. So we have used this diffusional model that depends on the chemistry to try to, it doesn't show much, but basically all these are points of alloys that we have simulated in the computer, and we have taken basically the rate of microtwinning and also the rate of climbing, which is the mechanism that is happening at high temperatures. And all these two mechanisms are the limiting processes for designing a new alloy. So these are the current patent alloy that has been patented 10 years ago. So our aim now is, with this computational model, is to push this forward into new alloys that has better properties at mid temperatures, because we are blocking these microtuning mechanisms. We have patented these compositions now, and now we are casting it to prove that experimentally we get the same results, or that they are better than the previous one. And basically the conclusions of the work is we have studied underlying physics of the mechanism from a multiscale experimental point of view. The microtuning mechanism has been rationalized and physically modeled in the continuum model. And we have studied the single crystal creep behavior of this alloy I have shown before, and it has been studied numerically, and we have also used this model to propose new grades of alloys that are currently under testing. So I would like to thank you, all of you, for coming.